Okay, I guess we can get started with the second session, and we'll start by hearing about GAN from by Luke Oliveira.
Well, thank you all for coming. Hopefully we're all caffeinated. I know I am. So I'm going to talk about GANs, Generative Adversarial Networks for Simulation. And this is joint work with Michaela and Ben, who are from Berkeley Lab with me. And yeah, I'm going to give you guys a brief overview of what we've been working on, kind of what the future looks like, and give you a little bit of an in-depth introduction into GANs for simulation. So the first thing I'll talk about is migrating from jet images, which we saw in Ben's plenary this morning, to calorimeter images. I'll describe an open data set that we've released for research at the intersection of ML and HEP. And then I'll go briefly through two applications, classification and regression, and show how those kind of fall from our data set. And then I'll do a much deeper dive into generative modeling, in particular focusing on CalOGAN, which is a method for fast calorimeter simulation that we introduced a few months ago. So, jet images are essentially a way where we can unroll a detector and all the depositions that we see within it into a 2D grayscale image. And for a much more detailed explanation of this, I highly encourage you to consult Ben's talk from earlier this morning. There are a lot of little details and unique characteristics of jet images, but they are physically motivated, and we are essentially looking at a 2D pattern of radiation within a jet. As you can kind of see here, these don't look like natural images, and it turns out to model these very well, we have to do some little tips and tricks from an ML side just to make things work out. There we go. We can shift from jet images to calorimeter images, which are a similar idea, but essentially we want to just, for the sake of pure algorithms research, we want to look at calorimeter snapshots purely as a 3D longitudinally segmented image. And there are some challenges that come with this. So calo images have high degree of sparsity. They have a high dynamic range. Inputs can span many orders of magnitude. And there's a certain degree of location specificity. So shifting pixels actually changes fundamental physical qualities and properties of these images. And this gets us closer to raw detector data, which is something nice. And this is another theme from Ben's talk this morning, which is people are moving closer and closer to raw inputs, allowing ML algorithms to, in particular deep learning algorithms, to shine there. And there are some advantages of a calo image-based representation. In particular, we have compositionality. So instead of having to simulate the full-blown event with all calorimeter depositions, we can simulate one and add them together. And we have nice quantifiable properties, so low-dimensional manifolds that we can validate performance on, see how well we are doing. That's fairly unique from a generative modeling standpoint. We usually don't have that. So just to kind of frame this, what does an electron look like inside liquid argon calorimeter? So we have an idealized calorimeter shown here, simulated with Jan4, and we simulate exact XY coordinates, XYZ coordinates of particles as they decay. And what we can read out is what we see on the right. So these are summations within cell. So obviously we lose a bunch of position information, but we wanted this to be as close to a realistic scenario as possible. So our data set of calorimeter images that we're releasing for hopefully people to do research on, it's a 3-layer heterogeneous segmentation resolution similar to, it's modeled after the Atlas detector. And we include 3 types of particles. We include pi plus, E plus, and gamma. And we also include variable position and variable incidence angle into the calorimeter, which is obviously a much more realistic scenario than just completely perfect pixels. And this is open, available, reusable, and citable. And for, if you download my talk, you can click on the little Zenodo link over there, and that'll take you to a place to go and download the data. So a quick rundown of tasks that we've kind of outlined for this. Obviously, I'm going to be focusing on generation in this talk, but quickly, this data set can be used for classification, regression, and generation, and hopefully people think of other uses we haven't thought of yet. That would be fantastic. It's simple, and it's in HDFI format, so it's nice and well documented. So hopefully no one has to struggle with any weird formats. But essentially, we want to start with classification, and we just want to quantify how well we can do on E plus versus pi plus and E gamma classification. And we want to compare some just basic benchmarks. We're not trying to do a full study here, but we want to train networks on raw pixel representations. We want to train them on shower shapes, which we heard about earlier in this track. We want to train more kind of traditional convolution style, which is something that's inspired by our original paper on GenImage GANs. And then we want to train a dense net, which is a new fancy way of having very parameter efficient image models. So for E+ versus Pi+ on calorimeter images, you can see we actually get a very nice performance boost from using a deep learning approach directly on raw pixel levels. So around the 98% efficiency operating point, we have about a 50% improvement compared to building a model directly on shower shapes. That's quite an interesting performance bump. We're obviously not going through and understanding this to the full extent. This is more to kind of motivate you guys going off in this direction and also using this data set for your research. And similarly on E-gamma, we don't see a 50% performance bump, but we are seeing about 7% improvement across interesting efficiency spectrum, further validating that we should probably consider at least some level of research down this direction. Very related to classification is just a peer regression task, which is show me a calorimeter image. Can I get back out what theta and phi were? And obviously, once again, we're not going into super high stats here. We're not looking at all the fine details, but we can get a very good sense that we're able to kind of predict along the y=x line and able to recover these quantities with a fair amount of fidelity. This doesn't have to be perfect right now. This is just to motivate the usage of this data set. In particular, one thing that we'd like to do with any generative model, which I'll talk about later, is to be able to condition on physical properties such as position and angle. So if we can't do these well at all, that would definitely be a problem for being able to condition on it down the road. So the meat. The meat of this is going to be on GANs and using them for simulation. So let's get a little bit of an introduction into generative adversarial networks. Like Ben described earlier today, it casts the task of generation into a game. It's a non-cooperative game between a discriminator and a generator. A generator is tasked with mapping some noisy latent space into a space of credible samples. And a discriminator is tasked with deciding whether or not a sample that it sees is drawn from a data distribution or drawn from a synthetic distribution. This is a nice little diagram of the system. And these models have seen a lot of success in natural images, so generating pictures of horses, cars, handwritten digits, things like that. And very recently, some work by us and some other folks at LBL, we've been working on some scientific applications of GANs, which we think is quite exciting. So the standard GAN formulation, this is the vanilla GAN, is we have some latent space that we're simulating from some distribution. It might be uniform, might be normal. And then we have a generator, which we want to map that latent space to some space of synthetic samples. And this lives inside our big space of all possible samples we could ever see M. So this is the guy that is trying to produce our samples. And in the case of physics, this is something that's going to have to take in some context and produce a valid calorimeter shower. Then we have our discriminator, which maps this entire big space to the real line between 0 and 1, which tries to tell us how real or how fake looking a particular sample is. And these two are the symbolic players of this generation procedure. So we construct a system that encourages these two players to have good behavior and to produce a good generative model. So how do we do this? We construct a loss with this green term up here, which is basically the probability, or related to the probability, that a fake sample is classified as fake by the discriminator. And then we want to consider the probability that a real image is classified as real by the discriminator as well. And this entire system gets minimized by the generator and maximized by the discriminator. And as you might imagine, the system can get, the behavior is not defined, but these two players are going in direct opposition to each other. So if we allow the discriminator and the generator to be drawn from the space of all continuous functions, clearly we can't do that, but if we could, then there exists a unique Nash equilibrium, and this Nash equilibrium results in G exactly recovering the data distribution, and the discriminator outputting a probability of 1/2 in the union of everything from the data distribution and my synthetic space. So this is all kind of pipe dreams, unfortunately. It says we can't have D and G drawn from the space of all continuous functions. So what happens in practice? The standard formulation that I described 2 slides ago is actually highly unstable. Optimizing the generator is fully bandwidth limited by how well my gradient propagates through my discriminator. In particular, if my discriminator does a very bad job or does a very good job, my gradients can get totally squashed and I'm unable to produce good samples. We also suffer from this problem called mode collapse, which is essentially the case where my generator learns 2 or 3 little discrete subsets of the support and learns to generate those really, really well. And that's obviously not very desirable. The other thing you end up running into is saturating discriminator output. So when the discriminator thinks something is very, very real or very, very fake, it has a hard time sending error messages back through to help the generator tweak its weights to do a good job. So these are all issues which are not exactly great. But there are a lot of solutions that kind of fall roughly into 2 categories. There are experimental solutions, which are more ad hoc, people kind of trying things until things work, kind of being intuitive. And then there are theory-driven or analytical solutions, which have resulted in some very interesting algorithms recently. In particular, I'm going to focus on the DC GAN formulation from the ad hoc side, and I'm going to focus on WGAN from the theory-driven side. So DC GAN is a soundless set of ad hoc, basically architecture construction guidelines for building these systems. It gives you guidelines around hyperparameters, layer construction, when to use batch normalization, when to use transpose convolutions, etc. These work really well for natural images. Unfortunately, this provides no theoretical motivation for why these things should work very well. We have a good rough intuitive sense as to why using a rectified linear unit that does not have sparsity should work well, but we don't have anything that we can prove. So WGANs, or Wasserstein GANs, on the other side, have a totally different approach to this, which is instead of casting GANs as kind of a art forger versus forgery expert, where a discriminator is saying, this looks fake or this looks real, we, at a high level, recast it to be an art critic, where an art critic is able to say to an artist, hey, this is much better quality or much worse quality, but on a scale that's not bounded. And that actually makes all the difference. So in the vanilla GAN formulation that I showed about 5 slides back with that loss function, implicitly, and I'm not going to show the proof of this, but implicitly that uses the Jensen-Shannon divergence to measure the distance between 2 probability distributions, which is great. But if we swap that with the Wasserstein distance metric, we actually get rid of some nonlinearities that kind of propagate through and lead to some unstable dynamics when you solve the system. So we always like to remove nonlinearity from systems. That's always great. And it turns out that WGAN does a very good job on a lot of problems recently. There have been some issues that have arisen. There's a new class called WGAN-GP, which does a very good job at getting over some of these mode collapse issues, but on the whole, the WGANs are very, very well motivated. So I will jump now into the LaGAN, which is our first work that tackled GANs explicitly for these jet images that we talked about before. And I'm only going to touch on this at a high level, but essentially we designed a GAN architecture that was well suited to jet images, so that means we're looking at location-specific features, we're looking at highly sparse images, we're looking at a high dynamic range, and we want to actually recover some meaningful physical distributions. And in particular, you kind of see on the right-hand side here, we reproduced mass and subjettiness quite well in terms of fidelity between generated and actual samples. And I'd like to emphasize that this was very much a proof of concept that kind of validated us going along the calorimeter trajectory. And we've talked about this a few times in Michaela's talk at the IML machine learning meeting. This is a link. Contains a lot more details that might be useful if you're thinking of doing something down this path. But the main takeaway from the LaGAN is that ML and GANs, all these newfangled tricks, and physics are not at odds. And we can incorporate prior knowledge and use our knowledge of what the domain looks like to construct architectures that make sense. So, the interesting stuff, CalGAN. So essentially this, I'm going to be kind of reporting on roughly what we had before, and then I'm going to go into some works in progress that we have going on right now. So for a full overview of everything that we've done with the CalGAN, GAN to speed up calorimeter simulation, I encourage you to look at this talk from DSAHEP. It goes very in-depth into all the little nitty-gritties of what we did. Today I'm going to give a high-level overview of what we did, but focus on architecture optimization and results on a data set with a more realistic problem scenario, which is varying theta and phi. And I'll also give preliminary results on a data set with variable phi, variable theta, and variable x and y initial impact into a calorimeter. So at a rough level, the cal again has 3 streams. We have 3 layers in our calorimeter. We have 3 individual components, one per calorimeter layer that learns what the deposition pattern should look like, conditioned on a particular set of physical characteristics. The thing that is unique about cal again is that we have a learnable attention mechanism. And this attention mechanism basically decides how much information to propagate from layer to layer to make it physical. And this is actually quite powerful in building models that understand sequential dependence. So this is a nice little schematic of what the cal-again architecture looks like. But essentially, you can see up here on the right, originally we were only conditioning on energy, so we would request a particle of a particular energy. But now we're incorporating, like I said, theta and phi. So we have a whole laundry list here of different hyperparameters that we're optimizing over with respect to trying to make this as good as possible for a real-world implementation. I'll leave these here and just for the sake of time, skip over that. The 2 major open questions that we have in using GANs to model calorimeters is how to appropriately model variation in the initial impact location, x and y, and how best to encourage the right level of sparsity. These are our open questions that we still have. So to evaluate performance, we like to look at average images in all 3 of the calorimeter layers. And this is actually showing a 5-degree variation in theta and phi, no variation in the initial impact position, and we're varying energy between 1 and 100 GeV drawn randomly. So we do a very good job of modeling, in particular the location specificity. We see some noise around here, so we're not exploring all parts of the data distribution, but this is very encouraging. And given how fast these algorithms run, this is a very good sign. And something you do in GANs to validate how well you're doing, not at the global level, but at the individual level, is you look at nearest neighbors. So when we look at varying the angle and the nearest neighbor, we look at the nearest neighbors under that, we actually find very nice preservation of rough sparsity levels. We have a very nice understanding of sparsity in the second layer. The third layer obviously has low energy deposition, so it's a little harder to model, but it's definitely very encouraging. But sparsity is a unique little guy because we actually do a very good job of exploring the whole range of sparsities, but the actual distribution of sparsities is very hard to uncover. And this is because you have a choice of modeling sparsity with a hard analytical version or something that's a soft approximation to sparsity. So this is definitely something that we'd love for you guys to use the data set and kind of explore with us, how to get the sparsity per layer looking a little bit better. Because I think this is one of the last hurdles before cal-GANs are directly useful within a collaboration. So like I said before, we have these shower shapes that we can model and look and see how well we're preserving underneath some simulated model versus our data distribution. And it's kind of there are some shower shapes that we do a very good job on, some shower shapes that we don't do as good a job on. But something that's important to keep in mind is that any shower shape can actually be baked directly into the training. So we choose to not bake any of these in, and any learning that happens here is done entirely just by itself. So we can actually, let's say we decide that we really care about sigma naught and sigma 1. We can actually bake those directly into our training and hopefully preserve those. This is the same plot on a linear scale. In the sake of time, I'm going to skip over this, but essentially what we're doing is we can project our distributions on a low-dimensional manifold and look and make sure that we don't see any clusters of GAN versus JAMP, which is kind of our ground truth here. We don't see any clusters, which is a good sign. The final work in progress that I want to talk about here is conditioning on the X and Y impact positions themselves. The spread around the initial impact is much larger here. This is actually a very hard problem. We have to disentangle the angle of approach from the position of approach. And this is something that we're actually still actively working on. So anyone who wants to participate, you're more than welcome. But we can see here with our nearest neighbor plots, there are some deficiencies. So in particular, we're not as good at matching the level of sparsity in the second layer. We do a very good job of getting the location right. So we're able to kind of fully explore the full space of kind of center of mass, but getting the sparsity around it correct is still kind of an open question for us. So we made a cute little web app to explore how using a GAN like this in practice might look. This is fully conditional, so you can actually visit this website. Don't everyone visit it at once because you're going to take it down. But you can actually tweak all the parameters that are currently available right now in like our current best model and you can tweak the theta, phi, energy, number of showers. And you can imagine an application like this in an experiment where you're actually able to request all these and have a GAN speed up the process. All of our code is open source. Dataset and analysis code is all available. There are Docker images everywhere if you want to reproduce things. Please visit our GitHub with repositories for both the Jet Images work and the CalGAN work. Hopefully that provides some inspiration. Yeah, and thank you. Hopefully this is a good introduction to
you said a couple of slides back, I don't remember exactly what slide number, that there were a couple of distributions but that you don't match well.
Yes.
Because you specifically are not training on them. Why not, or baking them in, as you put it, which I assume means they're not part of that discriminant likelihood. Why not?
Mostly just kind of to assure ourselves that we're able to learn these by default. If we were able to model our distribution perfectly, all of these would be well modeled.
So what you're expecting is that some other terms should have effectively taken care of these because
Ideally.
it has something to do with the shape or something. Should have. Okay.
Yeah, but these are like fairly nonlinear. So we're doing a pretty good job. I didn't really get a chance to go into it very much. Right here, we're using kernel PCA to find a nonlinear lower dimensional space, and we don't see any clusters there. So there are nonlinear projections under which our distribution generated by the GAN and the data are nearly identical. These ones, not necessarily the case. But we'd like to see how well we can do on these without telling it anything about that first before we start baking it in.
Right, but I guess one of the things you have to do is determine which ones are important for you
Exactly.
again, right? Which it could be you fix two of these and the others will also shape up because of
Right.
some hidden correlation.
Right.
I've got another question, but others should go.
Other questions? Yes.
Could you go back to your practice
Yes.
and explain a bit what you do construct?
Yeah.
Okay, so this is, I'm an applied mathematician, so this is probably where this comes from. So sparsity is, in this case, number of non-zero pixel activations divided by the total number of pixels. Occupancy. Occupancy, yeah, sure. It's just, yeah. Okay, cool.
Well, so the basic question, so the conditioning.
Mm-hmm.
So essentially, we don't just want our simulated jet to reproduce a subject. We want it to reproduce with that energy, at that angle, with that values. And those parameters is a long list, and most of them are just hidden. For example, well, jet shape depends from jet from T channel depends from T. So in particular in that mode. So is it correct that those simulations are limited to those conditions which are listed in advance and are not and cannot reproduce those hidden conditions?
Yeah, I mean, you're definitely limited by what, if you're talking about purely like class conditional things, you're absolutely limited by discrete. Unless you've shown it something beforehand, you can't expect it to reproduce it. In terms of modeling, I think what you're getting at is modeling the tails of things if you haven't had enough data samples to see something out there.
Well, it's not,
Okay.
there are parameters which affect jet directly, strongly, but we did not put it in our model web frame.
Yeah, so I think it's a different question. So this is actually not about jets, it's single pion. So single pion showers are totally determined by their position when they hit the calorimeter, the energy they have, and the particle type. Nothing else.
Okay.
Time for one short question.
Well, there is no utilization.
One additional-
But it is specific. So in general, would this approach be extendable for full range of conditions, or it is a principal limit?
No, you can add more conditions.
I mean, you can have as many conditions as you want, right?
But those all conditions must be selected in advance. right?
Yes,
So we
yes, they
get
have to
to
be listed in
priority.
you can't condition on something that was not known a priori.
Well, if this is a short one, we've got to
The
move
short
on.
one, in your open data set, which kind of geometry?
It's not the exact atlas, no. It's very close.
Well, it's not the according geometry, they're simple single layers of the argon on it, but
Just a toy. Okay. I think we have to move on because